Good morning, everybody. It's time to start. Welcome back. So this is the session, today's session, right? It's the fourth time we meet, and then we will meet 4 more times. That is tomorrow, Friday, and then 3 days next week. As always, this is recorded, and you can see in the Google Drive how to access the different recordings. If you check the Google Drive, if I share my screen with you, which screen shall I share? Yes, this one. If I share this screen and you go to the Google Drive, then you will find one place, one file, recordings of the sessions, the last files. And if you open it, then you will find that each day I add the link to the recording, and they will remain here for a number of months before they are deleted by the system at my university. So that's where you can find this. And if you check, I have added yesterday the text. So I mean the file, the R file that we did together yesterday with many more annotations. And then what we will also cover today, or at least partly today, is a new lecture, shorter one, on how to process syntax. And I will show you especially how you can do that quite easily in R. So that's what we can try to cover today. And maybe before we move to this lecture, we can review what we've been doing yesterday and maybe add a little bit more to that. Okay, does that sound good? Let me see if I have the chat. That should be here. This I can hide here. This I can hide. So I need to not get lost with all the things on my computer. All right. So let me open R, and let me open the file we played with yesterday. That should be around here. All right. So if you remember, if I open where is it? Okay, it's here. What we tried to do yesterday is to build, if my computer is willing to start. Yeah. What we tried to do yesterday is try to build a very simple spell checker based on skeleton keys. One of the key approaches we had seen together during the lecture on Tuesday. So we covered a number of functions, and then we were basically building the components of this simple analyzer. So if you remember yesterday, if I try to make this bigger, I zoom in twice. What we did yesterday, we investigated some function like unique and sort and to lower, to upper, str split with different ways to cut a string of characters into different components. I told you about the vectorize function, and then we saw how we can load a tabulated file, that's a dictionary in our case, with a number of word forms, correct word forms. And then we also loaded a text that we want to analyze. And since we want to build something based on keys, on skeleton keys, we basically build a function that we call getSkeletonKey, so that we can give any string of characters and get in return, get the skeleton key. We tried it, it was working fine. Then what we did also is we made sure that the correct words in the dictionary, they only appear once. That's why we learned how to use this function, distinct, that you could use in other data science approach, whether with text or not. And then we, for each word in the dictionary, we computed the skeleton key next to it in a second column. And what I told you, when you do that, either you make a loop, or you can use the function, a function directly and apply it to a vector of strings of characters. And what we saw is that when you do a loop, it takes way more time than when you don't. What we saw also is that our function get skeleton key. You cannot give it just a vector of elements and get the result straight away. It doesn't work like this because we did not write our function so that it is vectorized. So we use this function vectorized to create a new function, and then we could use it to compute the skeleton keys for all our words. That's here. So we use the vectorized get skeleton key. We provided all the words in the dictionary, and then we put that in a new column that we called SK, like skeleton key. And then, of course, our dictionary is ready. Then what we did, we built a list of all our words, and that's where we ended, because now we need to check these words one by one, and we need to check if they are in the dictionary, and if not, how can we use the skeleton keys to move forward. So that's what we did yesterday. I have a question. I have no access of downloading file in Google Drive. So I give you the Google Drive once again, the link to the Google Drive. You should have received it by mail, but maybe you are not in the list, but everybody can access it with the link. So that should be okay. So Google Drive is here. So Diane, if you go there, you will find everything that is bound to work. All right. Are you with me? Is it good? Did you have time to check what we did yesterday? And shall we do the core part of the spell checker? That is, write something to check the words one by one. Is it okay?
Yeah, I think it's okay.
It's okay?
Yeah,
everybody?
good.
Do you have any question? Let me just turn on the light in my office in 3 seconds. All right. So this is where we stopped, to be continued. So now, basically, what we need to do is to check all our words one by one. So for that, we're going to keep things simple. We are going to use a loop. Opa. So we're going to use a loop to check our words one by one. If we want to create a loop like this, there are 2 ways we could do. We could do something like this. We could compute the number of words we have to check. The way we can do that is to ask for the length of the vectors. Of the vector. Oh, I need to execute everything before, sorry. Otherwise, of course, nothing is going to work. So I'm going to try all these things. So everything we have done before. All right. And now I'm going to use just this one. That's okay. Okay, we do this one. It takes a few seconds, and then we have our dictionary with what we, oh no, our final dictionary. Yes, this one. Okay, we have our dictionary and we have all the skeleton keys. That's good. And if we want also, we can enter the other thing, which is the length of the words, how many letters. And then we split our words. All right. So if we want to know how many words we have in our vector, we can just use the function length. And then if we check what is the value of words number, 65. So we have 65 words to try. So we can do a loop, and this loop will go from 1 to words number. So if I want, I could do something very simple. I could write something like this. If we do a loop like this, what do we do? Very, very simple. We just print the words one by one. And you can find the word. Hello, my name is Charles. I was born in London in 1988. So here is a very simple loop. We just use I like this. There is another way to do that, in which you don't use I. What you could do, you could just do like this. This is another option. You could write W or I. And then you are picking all the elements one after the other in the vectors, sorry. So if I do this, I get exactly the same result as before, except now that I don't need to use this, this value I. Sometimes it's easier like this. Does that make sense? It's just a way of writing down the beginning of the loop. I'm going to get this up. All right. So what do we need to do in our loop? We want to check whether our word, the word W, appears in the dictionary. How can we do that? Does anyone has a proposal regarding how we can do that? Please give me a solution to do that. We want to check whether our word W exists in the dictionary. How can we try to do that? What is the method we can use? Can anyone help me with that? Simple solution. Don't be shy. Just give me your ideas.
Hello. We baca.
No? Anyone? Okay. We have to use this operator indeed, but how are we going to use it? That's one way of doing it. What do we kind of need to do here? We need to go through all the words. Yeah. So if the word, but what do we need to check? We have all the words in our dictionary. So what do we need to do? Try to put it in simple terms. We would need a test. Yes. One way of doing this would be to do something like this. Maybe we call it W2 in, and then we take our dictionary, the one we had at the end, and we look at we take the column where we have the words in the dictionary, and we are going to look at them one by one. And then maybe we could say something like if W equals, or maybe we call it like this, W dict, like word in the dictionary. If the word is equal to the word found in the dictionary, maybe we could write something like word found. Okay, so if we found the word in the dictionary, we could write word found. But then if we don't find it, we would need to write like word is not found, something like that. You can do that, but it just requires some efforts. What would be very nice is that, let's say we have a vector with simple things like A, B, C, D, and I have target, and let's call my target A. And we can ask ourselves the question, can I simply check whether my target is in the vector? So we can do a loop and do it one by one and try to find that. It's possible, but there is most of the time a better approach than a loop in R. So if we want to check that, what we could do is there are different techniques here. We could try to do my vec equals A. Oh, sorry, my vec target equals A. If we do that, you see what we get? We get a vector of Boolean, 4 values, true, false, false, false. The first value is the same as the target, so we get true. All the other ones are different, and we get false. That's one way of doing it. If you want to know what is the index of this element, you could try something like this. Which of the element is true? That's another way of extracting this time the index, the position of the element that has been found in the vector. I show you the stuff we're going to use. What you can do is use this one. Here, if you do that, you will get true if the target can be found in the vector, and you will get false if the target cannot be found. Let's say the target now is Z, and we want to try. If we try, this time we get false. So we can do a test and know whether a word appears in the dictionary or not. It is not very difficult to do. We can simply use this in between percentages. There are many, many ways to achieve the same result. I just want to show you a simple way to do it. So here, what we could do is ask if the word appears in the words of the dictionary. That's how we can do the test to check whether the words is here or not. So what we could simply write is something like this. So I'm going to copy that above and leave it for now. So here we have a loop. We check all the words in my list of words. And then for each word, we check whether it appears or not in the dictionary. If that's the case, we say the word is in the dictionary. If that's not the case, we say the word is not in the dictionary. We can try that. So if we do that, you see what we have? Hello is not in the dictionary. My is not in the dictionary. Nam is not in the dictionary. Is in the dictionary. Charles is not. I is in the dictionary. And so on and so on and so on. Maybe I need to do something here. Do you have any idea that what maybe something I need to do?
birirwa bapereza kuri Trump ureba bakeneye kumunekaho cyane.
Maybe hello is not in the dictionary, or my is not in the dictionary because they have an uppercase later. So maybe if we want to check the things the best we can, maybe we could use lowercase for all the elements. That's a strategy. So maybe we could try lowering W, and maybe we could lower also all the words in the dictionary when we compare them. That could be something like this. Or maybe what we can do is we could do that before, so we do it only once. So we just say, okay, all the words in my dictionary, from now on, I write them, I want to, they are written in lowercase. So if I do it once, then I don't need to do it every time, and I save time, of course. So I put all the words in lowercase in the dictionary. Then I check my words, lowercase as well, whether they are in the dictionary. If I do that, now I find that hello is in the dictionary, my is in the dictionary, NAM is not in the dictionary, is in the dictionary, Charles is not in the dictionary, I is in the dictionary, and so on and so on and so on. Hong, like Hong Kong, is not in the dictionary. So you see, we find many words which are in the dictionary, and some words are not in the dictionary. So maybe if we just want to see the words which are not in the dictionary, so maybe that's the first, then we can single out the errors. Maybe we can just write when it's not in the dictionary. What we could do, if we want to just do that, we can just use this. It will take the opposite of the test. So this one, if you add the question mark first, that means if the word does not appear in the dictionary, then we can write it. So past 0 is just a way to combine a number of strings of characters together. So if I do something like this, hi, it will give me one string of characters only, composed of the two strings. If you write more than that, then of course it works with 3, with 4, with 5, etc., etc. So now with my new loop, I'm going to check whether the word is not in the dictionary. Then if that's the case, I'm going to write W is not in the dictionary. So if I execute this, what do I see? Nam is not in the dictionary, Charles with 2 S is not, the date is not, Hong Kong not, the two names is not, different with an E, city with the inversion, trying with the inversion, improve with the reduplication, competitions, and challenging. Do you agree with me that we have actually detected all the lexical errors? Not the grammatical ones, because that's not something we can do. So we detect all of them, but we have trouble with dates and proper names. I think something like that. So it seems that in our dictionary, we don't have like the first names, Theodore and Annie. But apart from that, it looks pretty okay. Do you agree with me that we find what we want with this approach? Does that make sense to everybody? We take our words one by one. Each of them, we check whether they are in the dictionary or not. If they are not, then we try to do something about it. So what is our next step? What should we do now? If you remember the global objective of this exercise, what should we do now? Some words, they are in the dictionary, no problem. For the words which are not in the dictionary, we want to do something about that. We want to suggest maybe plausible corrections. How shall we try to do that? Can you please give me how how we should approach this next step? What should be our next step? We have some words which are not in the dictionary. What should we do? What do we need to get right now to move forward? Anyone? Come on, don't be shy. Please, don't leave me alone. Give me some ideas. We need to compare the skeleton keys, right? Okay, so I'm going to restart from the same place. If a word does not appear in the dictionary, I should check things further with skeleton keys. Yes. Find plausible corrections. So I'm going to write some more stuff. If the word is not in the dictionary, maybe we print some information about that. Okay, no problem. Good. I'm going to make it just a little bit easier to read. I'm going to write like, I'm going to surround the word with a simple quote. So like this, you will see the word between quotes, just easier to read. So we need to compare the skeleton keys. So the first thing we need to do, we need to compute the skeleton key of our target word. How do we do that? We just call our function get skeleton key. And we call it by giving it the word W. Then what we could do, we could write something like the skeleton key for W is, and then we could give the skeleton key. Why not? If we do that, we can try. We run our thing. Very good. Okay. NAM is not in the dictionary. The skeleton key for NAM is AMN. Charles is not in the dictionary. The skeleton key for that is ACEHLRS. The skeleton key for whatever, like a different with an E. Okay, the skeleton key is DEFINRT. While we compute again, while we have it on our data frame, what we have in our data frame are the skeleton keys for the correct word forms. Here, I am computing the skeleton keys of the incorrect forms in my text. By definition, they are not in the dictionary because they are not correct forms. Otherwise, we find them there. We don't need to check skeleton keys. Okay? Right. Okay. What should I write here to check whether there are words in the dictionary which have the same skeleton key as my problematic form? How do I do that? I want to check whether this skeleton key is in the data frame. What should I write? How do I write the test? Given what we have seen just above, you should know how to write that. What is the instruction here? To check if our target skeleton key corresponds to a word in the dictionary. What should we use if I want to check that? Anyone? What can I use to find if my target skeleton key is in the table that I have? Nobody? Yeah? How do I write that? Before I had something like this. How do I transform that? Rather than the word, I have the skeleton key I want to check. But I don't want to check it in the words. I want to check in the column for skeleton key. Perfect. Okay. Okay, I can see what was proposed. Yeah. So if we do that, we check if our target skeleton key appears in the table. That's good. So if that's the case, maybe we could simply say, as a starting point, the skeleton key corresponds to a word in the dictionary. Why not? We can run this one. All right. So for the first one, okay, the skeleton key corresponds to a word in the dictionary. Interesting. For Charles, the skeleton key corresponds to a word in the dictionary. Okay. 1998, Hong Kong Theodore Annie, okay, but different. The skeleton key corresponds to a word in the dictionary. You see? So there are, I think most skeleton keys we have here appears in the dictionary. No? Yeah, so basically for nearly everything, we have the skeleton key. So now what remains to do is to propose some plausible corrections. So for that, each time that we find the skeleton key in the table, we should return the word, the corresponding word. So what we can do, we can add a few more things here. So I use this bracket because I want to put more than one instruction. If I have only one instruction, I don't need the brackets. But if I have more than one, I need the brackets to say, okay, if it's like this, then do all these instructions. So I'm going to say, okay, I want something that I will call corrections. And in corrections, I want to extract all the words which have the same skeleton key as my target skeleton key. So I am going to use my dictionary. I am going to access the column skeleton key. And to select the row, I'm going to say the skeleton key should be equal to the target skeleton key. That's one way of writing it in R. There are many different ways to write that. So I select only the rows where the skeleton key in the corresponding column is the same as my target skeleton key. And then I select for the column, for the result, skeleton key. So now I will have selected a number of words, and maybe I can print them. And then we are going to see what we get as plausible corrections. Does that make sense? I do it step by step once again. I created the loop for all my words. Then I checked whether these words, they appear in the dictionary. And when that's not the case, I compute the skeleton key. I look for this skeleton key in the dictionary. I mean, in our table, okay? And when we find the skeleton key, then, well, I get all the words that have this skeleton key and I print them. Does that make sense? Or do you have any question right now? Are we good? Yeah, yeah, all right. So we can try. Maybe if I print all the corrections like this, it is going to be quite messy. So I'm going to use something I have used before. I'm going to use past 0 with all these corrections. I'm going to write something like corrections, and I'm going to use one argument, which is collapse, which means I want to, no, not collapse like this. I want to put all the words in my vector corrections, and I want to separate them by a comma and a space. It's just a way to have something cleaner in the output. So now if I do that, perfect, it works. Oh, except I made a mistake. The corrections, they should not be the skeleton key. They should be the words. So that's my bad. All right, I'll try again. Okay, let's see. So if I have my word, my form NAM, it's not in the dictionary. The skeleton key is AMN. And the skeleton key corresponds to a word in the dictionary, actually several words. So maybe I should write at least one word in the dictionary. Maybe that's better. So I do it again. Okay, the skeleton key corresponds to at least one word in the dictionary. And you see the words that are proposed, man and mana. Do we see here the correction we would like to have, which is name? No, we don't find that, because the skeleton key for name is actually AEMN. So this method here is not very helpful for our problem. Charge is not in the dictionary. We get the skeleton key. There is a word in the dictionary, at least with this skeleton key, but you see the word is larches. I'm not sure what that means. Maybe some of you know. Doesn't work well either. If we try different, it's not in the dictionary. We have the skeleton key for it. This skeleton key corresponds at least to one word in the dictionary. And these are the possible correction. Different, indifferent, interfered, and a drift net. Here, what we can see is that the appropriate correction, different, is in our dictionary. Another word for city, I wrote CIYT. The skeleton key is actually CITY, and in the dictionary we have the word city. Actually, we have it twice. That's a little bit weird. Maybe I missed something I should have done. Maybe I missed a step, but that's what I get. This is the correct form, right? Trying is not in the dictionary. The skeleton key is this one. There is a word in the dictionary with the same form. That's trying. That's the correction we want. Improve is not in the dictionary. We have the skeleton key. Oh, one word has the same skeleton key. It's improve. That's exactly what we want. Conditions. Actually, the skeleton key is not in the dictionary, so we cannot propose any correction for this word. For challenging the skeleton key, we have it, we compute it, and we have a number of corrections. And in these 4 words, there is the word we are looking for. So you see, so I'm going just to make a small addition. So if I don't find the skeleton key in the dictionary, maybe I just print, well, the skeleton key does not correspond to any word in the dictionary. So if I try this again, one last time, for conditions, you see, I compute the skeleton key, and then the skeleton key does not correspond to any word in the dictionary. This is very raw as an approach, but do you agree with me that it works not very well, but not too badly? I think in my dictionary, I don't have proper names, but if I had proper names, that would also address some of the problems. I could also do something for numbers. I could prevent the looking for numbers in the dictionary. I could do that. That could make sense. Are you with me? Do you see how we have built the spell checker step by step? Is very rudimentary. So when people were using skeleton keys, of course, they would have many, many more small tricks to make it better. But you can see how we can do that. We did it step by step. So if I come back to this part, write a procedure to check if the word forms they appear in the dictionary. If they don't appear, check if the skeleton key corresponds to the key of at least one word in the dictionary. And if that's the case, return these or these words as plausible corrections from the erroneous form. What we could conclude is, well, it's not that bad, but it's not perfect either. What we could do, if we would keep the frequencies of the words in our dictionary, what we could do is to maybe suggest the more frequent words before the less frequent words. So we could order our corrections. Maybe that would help, maybe in most situations, but of course not all the time. That could be a small improvement. So that's what I can show you in a very step-by-step method to create the first step of a spell checker. We have used a number of functions in R to create the right elements that we needed. And then we have our central routine to make sure things are okay. What I will upload later on, I will upload this one. This is another piece of code that I prepared before. in this piece of code, you will find the correction, actually the stuff we have done already. Same stuff. You see, very, very similar to what we have done. But then maybe I don't do this now because it takes time and I want to tell you and make you try other things. But in the assignment, I have one part to go further and another part to go further. And actually 3 parts, but I've written the correction for 2 and 3 as well. So here in the part 1, if you take time and try by yourself, you will find that I have created a method, a function, to generate all the alternative skeleton keys for a given skeleton key. What I mean by that is what I told you in the course. If you take the skeleton key AICO, you could try to check all the skeleton keys with one difference only. You could drop the A. You could add a B. You could drop the C. You could add a D or an E or an F or a G or an H. You could drop the I. You could add a J, etc., etc. You can generate 26 keys like this. So if we use this, then we can try to go a bit further and we can look at all the words which skeleton keys correspond to one of these 26 keys. That's something you can do. So I will add basically some more lines compared to what I have done before. And the last option that you will find in my code is to use the Levenstein distance. And then you have a loop. You look if the word is in the dictionary or not. And if that's not the case, then you can look for plausible corrections using this time the Levenstein distance between the word and the words in the dictionary. And then you can compare whether the results are more interesting or less interesting. So I'm not going to decompose everything right now, but I advise you to go and check this and try to see whether it makes sense. I will double check everything before sending it to you, but that should work. Do you have any question maybe before we stop this practice? Did you learn something from it? In the end, that's always the question that matters.
Yeah, I think we are learning a lot of things, but I have a question because,
Sure.
like for the correction, you need to find all the possible alternative words that can be used in order to get correction.
Mm-hmm.
So is there, because I understand if you have something to do, you have first to create all the alternative words, or there is like a file that's contain many alternative words that people can just rope in that file. So, or every time you need to create your own alternative words.
What do you mean by alternative words? Sorry, so just to make sure I understand the
Yeah, for instance, you are talking like a Charles, and we can see on Scraton, and we see in the dictionary, we don't find it, for instance.
Yeah.
And then still you want to correct Charles.
Yeah.
So then, as you said, you need to make other alternative words for that can maybe help to identify Charles. Yeah, so that's what I'm saying.
Yeah. So actually the problem here is that my dictionary is not good enough, because I think in my dictionary, I don't have proper names. That's why I didn't find like Charles. There is not Theodore. There is not Annie or things like that. So actually, if you want to do this a bit better, you build basically a dictionary where you have like the one I have, like I have what, 90,000, something like that forms. But actually, if you want something more complete, you should rather have 400,000 or something like this. So I would definitely, if I want to be able to identify a correction for Charles, I would definitely, I think, need a dictionary where you have Charles, the correct form. Otherwise, the computer is not going to guess what is the problem. The computer can only compare and maybe compute skeleton keys and compare skeleton keys between some forms in a text that you provide and word forms in a dictionary. It cannot go beyond that in a way. So in my dictionary, I don't have Charles. Here, the problem is my dictionary is not very good.
I see.
Okay, so
Okay.
yeah. Of course, what we have done is super, super simple. People, they have been working on this for 20 years or more than that, or 30 years. Of course, the system that existed already 20 years ago, they were much, much better than what we've done. But at least we have done the basic, okay? But they will have much larger dictionaries. They will have all kinds of tricks. They will isolate numbers. They will know proper names, and they will do a lot of different things.
I see.
Okay?
Yeah, thank you.
But what is important, why are we spending time on spell checking, for instance? Is that if you want to do proper text mining, if you want to apply algorithms to extract the meaning or to extract the sentiments of a text, stuff like that, you want your text to be as good as possible. Otherwise, the tools, they won't perform very well. So if you can correct errors in your text in the first place, that is very much going to help later stages of processing. So that's really like an initial step in text mining. Correct the mistakes if possible. If your text is completely free of mistakes, then perfect. But very often there are mistakes. So maybe trying to correct them first is not a bad idea. Okay. All right. Okay. Okay. So I will upload this later today, and I will upload the corrections for the different parts. So you can check, and there is explanations and stuff. What I would like to do today is to tell you more about syntactic processing, and then we will try something very nice that you will find online, which is some functions you can use in R to analyze a sentence in English or in French or in Chinese or in Spanish or yet other languages. So we will use some functions in a package that is called UDpipe. And when you use this package, it's very powerful, it's really nice, it's based on deep learning, but you don't have to worry about that. It works very well. And you will see, I can show you how it works, and then you can try it. No problem. But in order for that to make sense, I need to spend maybe 1 hour explaining more about syntactic processing. So what I advise, it's 4 p.m. We take a 3-4 minutes break, and then I will start with this third lecture, which is not as long as the previous one, which is about processing syntax. Okay? So let's take just 3 minutes. I drink some water quickly, and then we go through this, and then we have some time for some activities related to it. So just give me a few minutes. I just drink some water to keep my voice. In 3-4 minutes, we will go through this one. All right. Okay, are you back with me? If that's the case, maybe we can check this shorter lecture, which is about processing syntax, or what we call morphosyntax. And I'm going to explain that. So this is actually what we could call a process flow or a workflow. If you would like to process language, if you would like to do some sort of language recognition, all the steps, there are actually two paths in a way. There is the path when you start with a vocal input, when you start with speech, and there is a path when you start with text. So the first path is like this. And the second path is like that. Depends what you are doing, depends what you start with. When you start with speech, with recorded voice, or with someone speaking in the microphone, there are a number of first steps. You need to process the acoustic signal. You need to extract some acoustic features of information that we call acoustic processing. Then from these acoustic features, you need to identify, let's say, segments, like the vowels, the consonants, the building blocks of the words. And we call it phonetic processing, and then we also have phonological processing. The two are very much related, and maybe I don't need to enter into details here, but that's how basically you extract the sounds which make the words. So let's call them the segments, the consonants, the vowels, the tones, or yet other things. When you have all these sounds, you need to extract the words, and then you need to make sense of the sentences. Or if you have a text, you don't need the acoustic processing, the phonetic processing, the phonological processing. You can jump straight to morphological processing and syntactic processing. And once you are done with that, then you can try to extract the meaning. That's when you do semantic processing, or you try to understand what is being said in the context of it being said. And that's what we call pragmatic processing. So the last two steps are about the meaning of what is said. But you see that you have a cascade of operations from speech, from the voice to the end. You may need to apply spell checking to the textual input. Maybe that will actually requires some morphological processing, sometimes because it can be a bit ambiguous. If actually, you may actually, if the text is correct, you may actually start directly from syntactic processing. The point is that from time to time, when you try to process things at one level, you have a number of ambiguities. You have a number of options, some competing alternatives, and you cannot solve them directly. So you need to move forward with your different alternatives through the next stages of processing. And then some of them, they are likely not to work. And then you can discard them until there remains like one option only. But that means that usually is not a forward process only. Sometimes you need to move to later stages and then come back. It's not that simple, basically. That's what I want to say. But we focus on syntactic processing and semantic processing when we do text mining, mostly. That's what we will do in the next lectures. And we have seen spell checking, which may be useful with textual inputs. If you wanted to specialize in natural language processing and speech processing, Of course, you would need to learn more about acoustic processing, phonetic processing, phonological processing, etc., etc. But let's say that text mining is part of data science, but phonetic processing, phonological processing, this is a part of NLP, which is not a part of data science. I think we may say it like that. So for us, it's not as interesting. Okay, that's the broad framework, but we don't cover everything. So our starting point is, provided that we have an input from a text, or, sorry, there is a mistake here, or after processing speech. And this text, this input consists of a number of words. How do we analyze sentences? And by that, I mean, can we identify what is the verb, the subject, the adjectives? Can we do that? Because that should be helpful to understand the meaning, basically. So that's our starting question. The problem, the challenge we want to address. So I've shown you various levels of processing. And in particular, you have what we call morphological processing and syntactic processing. The first one, the former, is the analysis of how words are constructed, the components of words, what we call morphemes, but I'm going to tell you about that in some minutes. And then we have syntactic processing, and that's the analysis of how sentences are constructed. And quite often, you consider that these two steps, they are related. So at least you should consider them at least in part at the same time. So that's why you will hear people tell you of morpho-syntactic analysis. So it's both morphological and syntactic analysis. They kind of go hand in hand. We are not going to pay too much attention to morphological processing, but still I want to emphasize this element. Why is it difficult to deal with morphemes and words and the structure of sentences? That's a general thing with all the languages spoken on our planet, is that they are full of ambiguities, and that takes place at different levels. On this slide, you can see how the linguists, they would use some symbols, some characters, but not only from the Latin alphabet. You see, there are others. How they would write the following sequence of sounds. 2 pairs of pairs. If you hear something like this, you will agree with me that you hear this, 2 pairs of pairs. It could mean different things. It could mean, but that doesn't make sense, 2 pairs, the fruit of pears. That doesn't make sense. But it could also mean 2 pairs of the fruit pear. That means in total 4 pairs. Or it could be 2 pairs of pears. P-A-I-R-S in both cases. So when you hear this sequence of sounds, you actually have a number of options. Some don't make sense, others do. Or you have the written sentence. The wind was too strong to wind the sail. You see here twice, you have the word which consists of the letters W-I-N-D. But the point is that actually here, I have a noun, the first one, the wind, and the other one is not pronounced wind, is pronounced wind, and that's a verb. So the same sequence of letters can be a noun, or they can be a verb, and the pronunciation can be different. So when we do syntactic processing, we want our system to be able to understand that the first one is a noun and the second one is a verb. How do we do that? That's the good question. We also have what we call structural ambiguity. Let's say that you hear the sentence, I saw the man on the hill with the telescope. I saw man, hill, telescope. All the words are non-ambiguous. It's not like wind and wine, what we have seen. It's not lexical ambiguity. It's an ambiguity when it comes to the structure of the sentence. Maybe you saw a man who had a telescope, or you saw the man because you used the telescope. And maybe the man was on the hill, or maybe you were on the hill. There are many options here, and you can see different cartoons, small drawings to illustrate these different options. If you have a sentence like this, it is very difficult to guess what is the right option. The only way to guess is to understand the broader context of the story, let's say, if this is part of a story. This is what we call pragmatics. This is very tricky for computers. It's less tricky for us because we are very smart and very good with language and with stories, broadly speaking, and explanations and text. So these ambiguities are tricky, and that's why the problem of syntactic processing is not so simple. So ambiguities can appear at different levels and they must be solved. If you can solve them, you get some kind of nice non-ambiguous description of a sentence. You know the correct words and you know the syntactic relationships between them. Okay, this word is the subject of that verb, and this adjective goes with this noun, etc., etc. If you manage to have that, then most of the time you have what you need to understand the meaning of the sentence. If you have Paul gives Mary a book, or Mary gives Paul a book, if you cannot have the computer tell you what is the subject, is it Paul or is it Mary? Who is the recipient? Is it Paul or is it Mary? Then you are kind of lost. You don't know who gives what to who. Sometimes you cannot know, like the structural ambiguity we saw just before. But if you can manage, then that's really nice. Then you can do a lot of additional things. So what do we need in terms of syntactic constructions to extract meaning? How do we do that once again? That's the question. So what you may learn with me today is to describe and exemplify ambiguity in language, explain the challenges when you do syntactic processing, and use a quite nice morphosyntactic analyzer parser in R. You give it a correct sentence, it returns the analysis of this sentence. Not 100% perfect, but really quite strong, like a 95% perfect or something like this. What I will cover, I will tell you a little bit on morphemes so that you understand this a little bit more. Then I will tell you about syntactic processing, and then a little bit about what we call lemmatization and part of speech tagging. And then later on, we will use these things to analyze the meaning of a text when we arrive on Monday and Tuesday and Wednesday. So that's what we will do. What I want you to keep in mind, once again, key points, morphological and syntactic analyses, they are the keys to extract the meaning behind the sentence. And actually, different languages will have different challenges. Linguists, they have their own methods to deal with that. but their methods are kind of difficult to use in NLP. Linguists, they like to build trees to represent sentences, what we call syntactic trees. This is very difficult for computers, but it turns out it's not that useful. You can do a lot of good, interesting things without that. That means that NLP doesn't need to follow what the idea, the representations linguists have, and to do exactly like in the standard, the classical linguistic analysis, the analysis that linguists are experts in. And you have different approaches which are possible. Some are based on rules, some are based on statistics, as in many other subfields of NLP. So that's what I would like you to keep in mind. Plus, learning how to do that with R. Not very difficult to do. So that's what I want to do. Once again, I want to cover a few words on morphemes. I want to tell you a little bit about morphemes. You know that without knowing it, maybe. Then syntactic processing, and then lemmatization, and what we call part of speech POS tagging. Are you with me? Is it okay? Or do you have any question?
Yes.
It's good?
It's good
So,
now.
Introduction, ambiguities, the task at hand, morphemes, sentences. That's what we want to deal with. But if you are not a linguist, maybe you know morphemes, you have heard of this, but likely it's not very clear. So I just want to tell you that so that you understand a bit better and why it's important to know that. Morpheme in linguistics, a morpheme is the smallest linguistic unit which bears some meaning and that you can isolate. Let's say that you have the word haircut. It's very clear if you speak English that you have hair and cut, right? You cut, you have your hair cut. So actually you could say here, this word is made of two morphemes assembled together, hair and cut. Can you subdivide hair into smaller parts which have their meanings? No. Can you subdivide cut? No. So you have two morphemes, smallest meaningful linguistic unit, hair and cut. And together you can make haircut. If you have singer, you have two morphemes. You have to sing, and then you have er, and if you think of other words, you will find that er, that kind of means designate the agent doing the action. Here, the action of singing. So you have two morphemes once again. Sing, singer. Clean, cleaner. To dwell, dweller, etc., etc. So you have two morphemes. And sing, you cannot cut it into smaller parts either. So you can see this is an idea of what a morpheme is. You have actually two categories of morphemes. And I keep things simple here because actually I could tell you way more about morphemes. But we have what we call the lexical morphemes and the grammatical morphemes. And that's not very far from orthographic spelling and grammatical spelling in a way. The lexical morphemes, they are also known as content morphemes. They convey some concepts, some conceptual information, actions, ideas, entities, persons, this kind of thing. If you think of singer, to sing, singing, song, singable, you can identify a common conceptual unit, which is related to the action of singing. It's all about singing. So it's kind of the root meaning, the semantic core, the core meaning. That's yet another way to put it. And linguists will tell you, you can have an infinity of things like that. You can always have new lexical morphemes in a language. It's an open list. And that's different from grammatical morphemes, which you can also call functional morphemes. And these things, what they do, they modify, they supplement, or they connect the meanings of content morphemes. But they don't destroy the core meaning. So when you have beauty, you can create the verb beautify. Or if you add full, you can create the adjective, the adverb, or the adjective, rather the adjective beautiful. And then if you add ly, you can create beautifully, and now you create an adverb. Or you have stuff like at work, under work, in work. These are grammatical morphemes. And this, in a given language, you don't have as many as you want. You have a list of them, and this list is bounded. It's a closed list. So this is more about the grammar of the language already. So lexical morphemes, grammatical morphemes. And some of these elements, they can have different roles. So affix is something you put in front or after another morpheme, to keep it simple. And some of the affixes, they are called inflectional, and the other one, they are called derivational. So affixes is stuff you affix, you add, you connect, you stick to a word, to keep things simple. So when we have inflectional affixes, this is about grammar. So that's what you use to tell about the tense, case, voice, aspect, person, number, gender, the mood, animacy, that's whether it's a living being or not, whether something is definite or indefinite, like the dog or a dog. And you can use them also to connect the words in a sentence. So in English, for instance, you have the dog barks. At the end of the verb, you have an inflectional affix, S, and it tells you that the subject of the verb is a dog. You have only one. So that's something about number, and that connects the dog with the verb, to bark. Or if you have ing, he's singing. That means that he's in the process of thinking. He's singing right now. It's something that lasts also for some time. You can also have stuff you add on adjective, like big, bigger, biggest, or the plural for nouns like dog and dogs. All these things are inflections. And then you have derivational affixes, and you use them to modify the meaning of a word or a part of what we call a part of speech. So that's when you add something like pray, this, in, un, full, able, meant, ly, eyes, stuff that you can add to other elements like happy, happiness. To dispose, prédispose. En français, in French, disposer, prédisposer. Or something like in French, parapluie. Para is kind of against, pluie, rain, umbrella. So you have a number of elements like this. You can use N to turn an adjective into a verb, like bright to brighten, strong, strengthen. There are a number of things you can consider like that. Or you can use un to create the opposite or the negation of something. Common, uncommon. Let me try to find another example. necessary, unnecessary. So you see that you can analyze, you don't need to remember all the details. But what I want to tell you is that when you have a word, you can look at the morphemes, the components of this word, and you can try to understand what they do. Do they help you to, in terms of grammar of the language, do they help you to change the meaning of the core of the word and how does it work? We have all these things, and in linguistics, we call morphology the subfield where you study all these things. And there are many, many, many things to be studied. So if you are doing NLP, the question is, how do you deal with all these morphemes? The point is that some languages will be maybe rather simple here, and some languages will be way more difficult. In Vietnamese or in Chinese, in Mandarin, the words basically, they never change. And you don't keep adding affixes, small pieces before or after. It doesn't work like that in these languages. So the morphology is quite simple. So it's way simpler than English and all the affixes I have just mentioned. Now, if you speak French, or if you try to learn, or if you have tried to learn French, you know that some parts of French are already crazy when you have to learn it, and when you didn't learn as a young child, especially verb conjugation. If you think of the verb chanter, to sing, infinitive form, chanter, chantait, chante, chantait, chanta, chantassiez, chantions, chantons, chantat. These are all possible conjugated forms of the verb. And you see that each time you modify the end of the verb, the final affix, the suffix, and that tells you about the tense, that tells you about the aspect, whether it's an ongoing action or it lasted only for a brief moment, the gender, the number, the person. It tells you a lot of things, but it's very expensive, very tricky, difficult to learn, which means maybe also not easy for the machine to understand. So some languages are easier, some languages are way more troublesome. French is quite troublesome, I would say, if you speak it very well, but if you start to think of how complex it is, then you realize. English is also quite bad, but some languages are actually simpler in this area, at least. But then they are more complicated in other areas. So morphology, something very rich. Some people, they work their entire life on things like that in linguistics. It changes from one language to the next, which means that it's a challenge for NLP because the recipes you might have for one language may not be the same as the recipes for another language. Different languages require different approaches. If you speak Mandarin, you cannot say in Mandarin 3 plates. You need to say 3 cylindrical object plates. You cannot say 2 cats. You need to say 2 animal cats. You cannot say 3 trains or 4 trains or this train. You need to say this vehicle train. And that's the same in Japanese. Actually, for all of you who speak a Bantu language, very likely you have something that you don't have in French or in English. You have what we call nominal classes. The fact that you have a number of categories of classes for the nouns of your language. That's something quite common in Bantu languages. If you want to do NLP with these languages, then of course you need to deal with that, and you don't need to deal with that in French. Does that make sense? That's something you need to pay attention to. What we have seen is that many of the morphemes, the grammatical morphemes in particular, they tell you about syntax. They tell you about the grammatical, the syntactic relations between the words. And that's how morphology is deeply connected to syntax. And that's why we sometimes put them together and we say morphosyntax. This suggests something important. If you want to analyze sentences with NLP tools, whatever the system you use, you will need to pay attention to the shape of words. In the languages where morphology is very rigid, nothing changes much. Okay, quite simple. But in French, if you can analyze the morphology of the verb and of the subject and the adjectives, etc., that's your way, in addition to the position of words, that's the way to analyze what is the verb, what is the subject, what is the object, direct object, what is the indirect object, who is doing what, where, with who, etc. So you need to understand how words are built, constituted, assembled, so that you can further analyze the meaning of a sentence. I put it very broadly. I just want you to understand this idea, this concept. Does that make sense? Are you still with me? Or do you have any question? Once again, do not hesitate to ask question. Okay, I try to be broad, I try to explain well, but sometimes it's not so easy. So I just try. Okay.
Good.
Good. All right. So morphemes. I'm not going to bother you more with morphemes, but I want you to know that this matters. Okay. We are not going to go into the details of the systems, but you have to understand that these are the kind of things that need to be accounted for, basically. Now that I have told you that, I can tell you a little bit more about syntactic processing. So what do you want to do? You have a text made of words, or you have sounds and phonemes, what we call the phonological sequence, the result of phonological processing that has been cut into, let's say, lexical units, cut into words. So what should a syntactic processor, or we could call it a syntactic analyzer, or it's also called the syntactic parser, what should it do? If you don't have text, written text, where you have punctuations to cut the sentences, basically, you would actually first need to identify where one sentence ends and the next one starts. So you will need to segment your input into sentences. If you have a written text, then if you write well, if it's well written, you know that you look at dots, question mark, exclamation mark, comma, etc., to find the sentences. That's the first thing you should do if you don't have at least a text already with punctuation. Then what you would like to do is detect the different groups, the different components of the sentence in each sentence, what we call the syntactic groups. The group corresponding to the subject, the group corresponding to the verb and things like adverbs, the object, etc. So what we call the verbal phrases, the noun phrases, the adjective phrases, you want to detect them and you want to label them to say, okay, this is that, etc. And what linguists like very much to do, they like to build some sort of tree for the sentence, a neat, a clean, hierarchical representation of each sentence. That's what linguists like to do a lot. And if you ask a linguist, that's what he or she would expect. if the computer would tackle the task effectively. Okay, that's what you want. That's what you wish you could have. And you might think of different approaches. The problem here is that linguists are very different from computers. And if we consider something like a sentence, for linguists, sentences are specific objects. For a linguist, a sentence is a relationship between a subject and what we call a predicate. And the predicate is a verb plus its objects, basically. That's how linguists would approach a sentence. That's a very, very linguistic way of doing that. But if you are rather a computational linguist, this is how you see a sentence primarily. For you, if you are a computational linguist, and if you remember what we have done before, if you remember all these things, okay, I'm going to use str, split, and then sort the letters, and then unique, and then this and this and that. What is a sentence? It's a string of characters with some typographic, let's say, cues to know the beginning and to know the end. Commonly, we have an uppercase letter first to start a sentence, and at the end, we have some punctuation mark. It's not always perfectly clear, but most of the time, you start with an uppercase letter, and you end with a dot, or an interrogation mark, or an exclamation mark, or 3 dots, but more or less, that's it. So you see that we are at very different levels here. For linguists, the definition of a sentence is something, quite conceptual. For a computational linguist, or let's say a programmer, a computer guy, that's very different. It's not about concepts, it's about characters in UTF-8, in Unicode, or in ASCII. And then you look for some specific things for the beginning and the end. And then that's inside, that's a sentence. So this difference in perception of what a sentence is, that explains in good part why you cannot directly use the ideas that linguists came up with in the past when they developed linguistics, why you cannot use these very nice, very formal ideas with the data you have. Linguists, what they like, I'm going to show you what linguists like. This is what linguists like. They take a sentence like le boucher sale la tranche. That's a French sentence. And they want to build this kind of tree. And that's when they're happy. They want to say, okay, boucher is a noun. Le is a determinant. And together they form what we call a noun phrase. And on top you have P, that's the predicate. And the predicate, I told you, is the subject. And then it's a verb with some other element. That's a verbal phrase. But you see, linguists, they like a structure like this. That's what they always try to build. We call this a syntactic tree. We call this a syntactic tree representation. The problem is that it's very nice in theory, and if you are a good linguist, you know how to do, although there are different theories and you might have different options for the trees, etc., etc. But there are many situations where it's very challenging to build a tree and to process a sentence. For instance, when you have things like the first words of the first line of the second paragraph of the fourth text of the fifth book. That for a computer is a kind of tricky. Or if you have things like noun phrase like the attics of the house that I bought are very dirty. This is also very tricky because the construction is quite complex. So a linguist will be able to build a tree, but for a computer, it's not easy. And you have stuff like this. Clarence loves dancing. We too. You understand that we too love dancing. But for a computer to understand that the two is basically telling you that we also love dancing, what we call an ellipsis here, because the verb and dancing, the love dancing is not repeated twice. This is also very challenging for a computer. So to build in a computer what the linguists like is a very tricky business. It's really hard. People tried and they have found solutions which are not bad, but it's definitely far from being perfect. So that's where we are. In a nutshell, syntactic parsing, as linguists may dream of it, is really hard. But maybe you don't need it anyway. So what can be done instead? So since attempts at producing syntactic trees automatically with computers have not been very successful, computational linguists, they have come up with something else, something simpler. They call it not full parsing. That's when you try to build a whole syntactic tree. They have come up with shallow parsing. They also call it surface parsing or robust parsing. The point is, what you want to try to get is a number of syntactic groups or chunks. So you may call the process chunking. And these syntactic groups, these chunks, you can give them some features. You can say, okay, it's a verb, it's this or that, but then you don't relate them in order to build a tree. So you don't create a full hierarchy. You create something like a structure, but which is rather flat. So there is no internal structure in your chunks, and the chunks are not related with a tree structure. There is actually a mathematical model for that. We call it a context-free grammar. That's a very important thing that was proposed by the very famous linguist Noam Chomsky, but I'm not going to push into details here. There is no point. That's just something simpler to do in theory and in practice. So if you see on the right, you have like a syntactic tree. We can also call this a constituent tree. And each time you have your words as the leaves of the tree, and then you group them and you create a structure. So you have these trees. And a tree is made of smaller trees. Everything is nested. That's the linguist's dream. This is what is really tricky to do. The other side, the shallow parsing, you will get something different. You will get what you may call is a kind of tree in a way. It's a dependency tree. So what you will have is not the full structure, but rather you will know the relations between words. If you have a full constituent tree, you can easily derive a dependency tree, but not the opposite. Because in a dependency tree, you have less relation. This is shallow. You don't go far up to the root of a tree or something like that. You may connect the words with each other, but you cannot build a tree in the same way as on the left side. This is full parsing. This is the stuff linguists like. This is the stuff that computers cannot do well. That's why computers mostly, they do the stuff on the right. Simpler approach, but actually quite interesting anyway. So that's when we are going to try something in R later. That's kind of what we will get. We will get a dependency tree, but that's not the same as the constituent tree. although we call it a tree. Some people call it a tree. This is chunks which are kind of connected to each other. When did people start to do that? Shallow parsing. That's quite old. That's more than 40 years ago. Nearly 40 years ago, in the 1980s. So they were trying that. And it's a syntactic analysis. It's not complete, it's partial, but they could cover a large number of constructions, of structures. So that was quite nice. But initially, in particular, you needed to correct the outputs by the computer. So some people, they tried to do that with algorithms, with programs, but the programs were not so good. Anyway, what some people did is that they took very large sets of sentences, of text, large corpora. Okay, let me try again. Let me finish this and I'll come back again. So they took large sets of text and then they tagged them with shallow parsing. So people manually, they paid the effort to create what we call today tree banks. So they took many texts and they taught people how to analyze them with shallow parsing. And then for all the sentences, they produced annotations, explanations for the structure. So for instance, in 1993, the Penn tree bank was released. And this is a corpus of texts, of sentences, of words, and they are 3 million words. But this was made very carefully. Maybe you used the computer first, but then you made sure that you corrected all the errors so that you have a very valid, very well annotated corpus. What is nice today is that when we have these corpora, we can use them as training sets to tag other inputs with supervised learning. So today, when you train like some neural networks or some other systems, you can use these tree banks to have training sets, to train, to prepare your model. And once it's done, then you can use it for other, to tag, to analyze any sentence of the language you like. Once again, to answer the question, tree banks, this corpora, it's shallow parsing. Shallow parsing is an approach in which you don't try to build a whole tree like that, what we call the constituent tree, but rather you try to do something simpler when you have, let's say, chunks, and you relate these chunks, you consider some relations between them, but you don't like create a structure in which you could have a root like you could have here. So it's something that is different, this stuff, from what the linguists are used to. It's just a simpler way to analyze the syntax of a sentence, how the words are connected to each other. Where is the verb? Where is this? Where is that? It can be pretty good. It can tell you a lot of things, but it's not as deep and it's not as rich as what standard traditional linguists would do. It still looks a little bit like a tree, but it's a shallow tree in a way. Does that make sense? All right. So let's choose shallow parsing because it's easier and it's still very interesting. How can we build a syntactic parser? How do we do that? I've told you before, you have rule-based approaches and you have statistical approaches. And that's true for many things in natural language processing. And now beyond that, if you do machine learning, you have some rule-based approaches and you have statistical approaches. A PCA, principal component analysis, it's a rule-based approach. A deep neural network, that's a statistical approach. Sometimes you have a number of words in a sentence and you end up with different competing alternatives to analyze the sentence. And both analyses, both interpretations of the sentence in terms of syntax, they are actually correct. So in French, for instance, if you speak French, you will see the point. Le boucher sale la tranche. That could mean first, the butcher, sale, salé, to put salt, salts, the verb, the slice, tranche can mean slice. I mean, in meat slice, it's a noun. Or actually another interpretation is le boucher sale, so the butcher who is dirty, because sale can be the third form singular of a verb, to put salt, basically, to salt something, but it can also mean dirty as an adjective. So it could be the dirty butcher slices it. And then tranche, this time, it's not a noun, it's not a slice, it's a verb. Slices, third person singular. And these two sentences are both, these two interpretations of the French sentence, these two more syntactic analyses, they are both fine. There is no violation of the rules of French, of the grammatical rules of French. So if you have a purely rule-based approach, where you just assess whether one interpretation is correct or not, you don't know what is the right answer here. You have an ambiguity and it cannot be solved. You could also find sentences like this in English. This one in French, I mean, if you speak French, it makes very good sense, but I think the explanation in English is also quite okay. In one interpretation, sale is an adjective and tranche is a verb. In another interpretation, sale is a verb, slice is a noun, and la can be the, but it can also mean something like it. Or it could be actually also like her, like if the butcher would be killing a lady by slicing her into pieces. Not very nice, right? Of course. Linguists, they would have two different possible trees for the same sentence. Do you see my point? If you just use rules which describe the grammar of the language, the two interpretations cannot be distinguished. You don't know which one you should choose. Are you with me? Does that make sense? It's just an ambiguity, because grammatically, both interpretations are just fine. But now, with statistical models, maybe you could say at least that one interpretation is more likely than the other. That a butcher is dirty and slices something, okay, it is possible, but I think it's much more frequent than to have a butcher who is always working with food, with meat, who is putting some salt on a slice of meat. That should be something that you say more commonly than there is a butcher who is dirty, who is slicing something. So if you have a statistical approach, which rests on how often some words appear with others, you should feel that the first interpretations is going to be the one that you should prefer, that the system will recommend over the other instead of the other. Just because, for instance, the noun butcher will often appear with the verb to sold, and this combination will be more frequent than butcher with dirty. It's still possible, but quite often when you tell people about butcher, it's more about preparing food than being dirty. Does that make sense? So rule-based and statistical approaches, they are both fine, but in some circumstances, maybe statistical approaches, they have an edge just because of how they work, because they work on frequent patterns, broadly speaking. So I won't enter into the details, but then you have actually rule-based approach to do shallow parsing. And you can use context-free grammars, very, very common model in linguistics, not the most complex one, but very well known, quite old. And then you have algorithms that you can use, like the Koch-Younger-Kasami algorithm. There are many things that have been developed, and that was developed before the statistical approaches. But then also you have statistical approaches, and we could enter into the details for many hours. You have what we call n-gram models, when you can measure the probability, the frequency of different pairs or triplets or quadruplets of words in very large corpora. And you can work with the words or with their grammatical classes. For instance, what you could have with an n-gram model, if you work on English, you could extract something like, if you have a definite article like the probability that after this article you have a noun or an adjective, the cat, the small cat, the house, the big house, the small house, the probability that you will get a noun or an adjective just after the article is very high. This is the kind of stuff you can encode in an n-gram model. And then you have more advanced things like hidden Markov models, where you model the probabilities of transitions between words. You can have statistical context-free grammars. Well, you can have a lot of things. I won't enter into the details, and I'm not an expert in that, but you have many methods to build a syntactic parser. For instance, you might use decision trees. That's another tool that you could use. Okay, many different techniques. We could focus on one, we could try to explain it, but then maybe that would take a lot of time and maybe you won't really need that in the future. Maybe what is more interesting is that you can use state-of-the-art tools which are based on these techniques. That's useful, right? So in a nutshell, the strategies for syntactic parsing in natural language processing, they actually are not the same as what linguists would do commonly, canonically. We use shallow parsing instead of deep parsing. We use dependency trees instead of constituent trees. We prefer simpler approaches. And there are techniques available for each strategy. If it's rule-based, you might use this or that. If you want probabilistic statistical approaches, then you might use probabilistic grammars. And something you might use, which works very well today, and there are many people working on that, you may use deep learning models. And on the right, you can see quite a crazy deep learning model where you have a lot of components and LSTM and well, is a tricky, complex model to try to learn how to do shallow parsing with any sentence in English, in French, in German, in Swahili, in Chinese, etc., etc., etc. The techniques are quite sophisticated today, and fortunately for us, now they work quite well. Are you still with me? I have a third part now, but you see, I have less to tell you about this. I don't want to enter into as many details. I want to keep it a little bit brief, and then we can play a little bit with something. That's my idea.
Yeah, we are following.
Yeah, we are together.
Perfect. Okay, good. So I can tell you a little bit more. I can tell you about something we call lemmatization and what we call part of speech tagging. Because you will see when we are going to do more text mining and stuff like topic modeling, things like that, we will use these things. So what is that? Lemmatization. That's an operation, but actually is easy to explain. It's just the name is a bit weird, but it's not very difficult. Usually, when you do a morpho-syntactic analysis, you want to take all the words and you want to describe them. And you want to give two elements. For each unit, you want to give the lemma, what we call a lemma in linguistics, and a syntactic, morpho-syntactic description. I'll give you a very simple example. If you have something like the dog barks, or the boy or the girl, the little boy, little girl cries. If you take cries, the verb to cry, verbs, if you have cries, you would like the system to tell you, okay, that's the verb to cry. And that's the lemma. And then you would like to know that is the verb to cry is a present tense, third person, singular, cries. So you would like the syntactic, morpho-syntactic description. So here you have two elements. You have the lemma, which is kind of the conceptual definition of the unit, like the morpheme at the core. Like if you have singing, singer, and everything, behind you have a lemma. It's like what you would find, not exactly in the dictionary, but kind of like that. The citation form, the way you find it in a dictionary, something like that. So if you have singers, plural form, if you go in a dictionary, you won't find singers. You will find singer only, because in the dictionary, you only have the singular form. So that would be the lemma. In a dictionary, you will have the verb to sing, but you won't have sung or sung for the past tense. So to sing would also be the lemma. And when you extract the lemma, the process is named lemmatization. So you want to extract that, and you want to understand how the lemma basically appears in the context of a phrase or of a sentence, and how that means how it is related to other words in the sentence. So that's the morpho-syntactic description. And quite often, what you give here is like the part of speech tag. And the process is called POS, part of speech tagging, or grammatical tagging, or word category disambiguation. So that's when you say the boy is crying. Crying is the verb. That's the grammatical category. So you might do that, or you might say, okay, so is present tense, third person singular. So that is a little bit more than that. And let me write something so I remember to change something later on. All right. So that's what you want to do. You would like a system that gives you that. That's what the systems they usually give you. So sometimes people, they say, okay, the lemma, they are the types. And that's different from the tokens. The tokens, they are the inflected forms. So when you have singers, singers, or chanter, chantait, chantat, chantation, chantassier, il chantait in French, these are the inflected forms, the forms with the inflections. And if you have to sing or chanter, that's the type, that's the verb, that's the citation form. Usually when you consider verbs, the lemma is the infinitive form. If you consider adjectives and determiners, the lemma is the masculine singular form. For nouns and pronouns, that's the singular form rather than the plural. So if you have dogs, the lemma is dog. If you have ate, the lemma is eat. If you have we, the lemma is I, masculine singular. If you have joli in French, IES, so that's feminine plural form, then the lemma would be the masculine singular form for beautiful, joli. That's the way it works. Some people would be unhappy maybe that why we should always choose the masculine form rather than the feminine. Okay, and there have been some movements to change the language for like to have a more inclusive orthography, things like that. That's just the way it is in the dictionary. And that's what people in NLP would follow, regardless of some broader philosophical conceptions we might have about that, or social considerations. So this is the lemma. It's not that difficult in practice. That's quite straightforward, actually. So once again, if you do POS tagging, you want to try and have a morphosyntactic description for each word. That's what I have told you already. There are different systems of tags. You may come up with different sets of categories, of grammatical categories. A lemma means a root word. Yes, in a way. It's kind of the core meaning, the root of the word. If you have dogs, the root is dog, right? S is just the plural. So the lemma is kind of the root. Yeah. Yeah. In some languages, some words, or actually many words, they will belong to several categories. You remember we have seen the example, le boucher sale la tranche, the dirty butcher, the butcher sold. So you can see that some words, they can be treated as a verb or as a noun. This is common in French. This is also something you find in English and in other languages. To run or a run, or it, like it creates trouble. It's a nominal personal pronoun, but you could also use it as a relative personal pronoun. So a slightly different category. So you want your morphosyntactic analyzer to be able not to get confused. Otherwise, then of course you're not so happy with it, right? So that's what we try to do. I just show you, if I mentioned the pen tree bank project, that people, they annotated everything carefully. These are all the categories, the parts of speech that they considered in this project. You see, you have NP 14, proper noun, and they said singular. Then they had FW for foreign word. Why not? They had adverb, comparative, adverb, superlative. They had WH pronoun. They had verbs, different kinds of verbs. They had nouns, etc., etc. Sometimes you have even more than that, and sometimes it's simpler. It depends, okay? When we are going to see the stuff in R, you will see the kind of categories we can play with. That's just one quite complex here example. That's for the pen tree bank. And you might recode this with less categories. This is, I think, a little bit too much in a way for most of the applications. So once again, if you want to do lemmatization and POS tagging, you may consider rule-based models, you may consider statistical models. This is very much related with parsing, broadly speaking. You may combine rules and statistics. You may have a limited number of rules in rule-based models. You may have n-gram models, hidden Markov models. deep learning, semi-supervised learning, decision trees, gradient boosting, you name it. There are many, many techniques. Today, what works best? Deep learning most of the time. You can compare all these approaches. So you can compare rule-based taggers and statistical part-of-speech taggers. The first one, rule-based, is kind of closer to traditional linguistics. The precision may actually be very high, but if you want to get very, very high precision, it's very costly to create. And you create it for a language, and it only works for this language. Well, that's a problem, right? Now, if you look at statistical taggers, they have a good theoretical framework, but it's not as linguistics, maybe. The models are usually more generic and simpler. The precision is not perfect, but it's like pretty high, like more than 97%, but that's not as good as 99.5, right? And what is nice is that the model is generic, so it works with one language or another. The same, let's say, deep neural network may be trained with data for French or with data for Dutch or German. Of course, to train the model, you need a lot of examples. It's not perfect either. So it's not like everything is black and white. It's more like a matter of gray tones. But I would say statistical taggers, they may be winning the game right now. I would suggest that. But we can compare different aspects. The first post tagger that was built is actually quite old already. And that relates to something that is quite famous, which we call the Brown corpus. It's 1 million word. It looks like a lot. It's actually not that much, but in 1961, that was actually pretty big. That was the University of Brown, with some people who behind William Nelson Francis and Henry Kuchera. And they wanted to kind of understand better how American English looks like, let's say. And they wanted to tag the corpus. They needed that to better understand the profile of American English at that time, a synchronic profile at time t. But the point is that it was 1 million word. It was too time consuming to tag everything manually. Plus, when they would tag, they would feel bored, they would get tired. If different people would work, maybe they would do it slightly differently, so it would not be very homogeneous. So you had quite a high risk actually of human errors because of the volume of the task. So, and if you did automatic tagging at that time only based on dictionaries, there were too many ambiguities. So some scholars like Green and Rubin, in 1971, they created an automatic tagger and they called it Tagit. And it was correct 70% of the time in the initial trials. So what they did is that they made it work, and then they analyzed the corrections, and rather than tagging everything from scratch, rather they verified and corrected the automatic analysis. And they did that a number of times until they reached something very accurate and complete. So that was in the 70s. So that's 50 years ago now. That's quite a long time ago. The first post part of speech taggers, like Tagit. Today we have better tools. One that is very well known from 1984 by Helmut Schmidt from Germany is called Tree Tagger. And this tool was created for quite a number of languages. You see, of course, don't expect to find small African languages, small meaning not so many speakers, or small languages from Africa or Asia or South America, but at least you had German, English, French, Italian, Danish, Dutch, Spanish, Bulgarian, Russian, Portuguese, Galician, Greek, Chinese, Swahili, Slovak, Slovenian, Latin, Estonian, Polish, Romanian, Czech, Coptic, and Old French. And actually, if you have data for other languages and you have a manually tagged corpus, you can train TreeTagger, and then it would work on new sentences of your language. It's a statistical approach, and it was based on decision trees, which is one way to do machine learning. Accuracy above 95%. Not bad at all, right? So that was TreeTagger. This is quite well known. And that's the end of what I wanted to tell you today before showing you how to do it in R. Are we good? Is it clear enough? I tried to, once again, I don't want to enter into very technical details. I want you to grab the challenges and the opportunities, basically. So what I would like you to know is if you are learning more R and you would find useful to use something like this, like something like TreeTagger, how can you do that? And I want to show you that actually is not difficult. It's not difficult at all. Maybe we take a few minutes as a short break, and then we take 30 minutes. I show you how to do it, and then you can play with it by yourself. Does that sound good? Okay, so let me just quickly drink and rest my voice, unless you have a question now, and then I'll show you how you can simply do that in R. All right, so see you in a few minutes. I try not to get too tired.
kandi ntabwo muri plan uzashyiremo ibintu byo gufayiringa amafoto afata umwanya amafoto yose ari ku ma social media nahe ushyire muri ya mafoto ngwino ndebere nk'aya ya Philippe umubwire ko yunamye ndabona yamwanditse itaburiya ayejo na taburiya yari yanze aha nkiyisaba ndayagufowadinga ya nkiyise sawa ya ejo yanyeje nsheretse ambwira ngo aya ntabwo twayakoresha bambaye masike na ndaza kujya ahise si ibyo ngibyo aya mafoto twakwiyeranjamo cyese mbimwohereze byose cyangwa namwoherezamo ingeri selection si ukumurushya ajya kongera kureba amafoto yose urakije. Yari afite amatsiko yo kumenya igihe uko yabonye bitagabanutse. N'umuntu ufite amatsiko yo kumenya ko ariko byadusabye acrobacy no kujongera n'ibintu. Ariko deni pari harimo sanse ariko nyine byasabye ko tujongera n'ibintu.
All right. I'm back. Let's finish the session for today with this, and then you can actually try to play with it. Today, we have better things than Tree Tiger because people have worked on better tools, and something that is pretty nice, like really not bad at all, is called UDPipe. UDPipe is something you can use in R. And in UDPipe, you can choose between a number of languages. So it means that this tool, the functions of this package, they can analyze, they can work with different languages. It works with Afrikaans, spoken in South Africa, Ancient Greek, and you have different versions, Arabic, Basque, Belarusian, Bulgarian, Catalan in Spain, Chinese, Coptic, Croatian, Czech, different versions, Danish, Dutch, English, Estonian, Finnish, different versions of French, Galician, German, Gothic, Greek, Hebrew, Hindi, Hungarian, Indonesian, Irish, Italian, Japanese, Korean, etc., etc., etc. So you can see quite many languages from different parts. Unfortunately, that doesn't include much African languages because I think we suffer from a problem of under description and we don't have enough corpora to do that. That's the pity. But still, it's valid for quite a number of languages in different areas. So it works the same with any of these languages. What you need to do to make it work is load the model, the language model of the language you want to work with. How do we do that? I've written a small piece of code and you can find it in the Google Drive. 3 morphosyntax processing.r. What you need to do to make this work is to use one package, which we call UDpipe. So here what I wrote, this small thing is that it's if you don't have UDpipe already installed in your computer, install the package. So if you execute this line in RStudio, you will install UDpipe on your computer. In my case, it's already here because I've installed it already. Once I've done this, if I want to use the functions in this library, I just need to write library UDpipe. And the first time you want to use the system for a given language, you have to download a language model. So if you want to work with English, you need to download the model for English. And actually, what is it? It's kind of the connections for a deep neural network that was trained for this language. So you want to work with English, you write English. You want to work with one of the other languages. Yeah, I mean, you could put that here. Okay, I'm going to. Okay, but if you type UDpipe on Google, you will find all these things pretty easily. So don't worry too much about that. It's easy to find online. So if you want to work with English, you could try English. If you want to work with Portuguese, you write Portuguese. So the first time you need to download it, and there is a function which is called UDpipe download model. You provide the name of the language, and you tell where you want to store the model. You give the folder. So in my case, I want to put it in D. Why not? You put it wherever you want on your computer. So let me go there with you. All right. So this is my D in my folder. And you see, okay, there was something. Okay, there is dictionary and text for spell checking from before. And now if I use the command, this one, oh, okay, I need to do my folder, sorry, my folder, download. And then it takes a bit of time, boom, it's download on my computer. And if I go in the folder I've just mentioned, now you can see that I have a new file and you see the name of the file, English EW2. The name is a little bit complex. That's the file to process English. That's it. If I want to process Portuguese, I just write Portuguese here. And then takes a bit of time. If I go there, now I have the file for Portuguese. Not so big file, not so small, like 15 megabytes. In Python, I think in Python you can use UDpipe as well. And in Python, they have another one that they use quite a lot. And right now, I forgot the name of this, of the other one. But what I can tell you is that I read some papers comparing UDpipe and the other one. And the conclusion was that UDpipe was better. So in Python, you can use UDpipe as well. All right, I think if I type Python and UDpipe, yeah, you will find it. It's here. Oh yeah, the other one they use, the other one you can use is called Spacey. Spacey is another set of functions and stuff that you can use for text, for something like this in Python. I guess you can find it also for R, but I don't use it. So you download the models you want. Once you have the models downloaded, when you want to use a language, you need simply to load the model. So I have checked that the model that was downloaded was English EW2 and I have the name. What I just say is that, okay, please, I load with the function UDpipe load model, please load the file in the folder. So you see, I use space 0 to combine the name of my folder with the name of the file, and then put the result in an object, in a variable. I called it my language model. Why not? So I do this. Oh, it's not the right model. So let me copy the name how it should be. I'm going to copy this because you see from time to time, the name of the file will change because they come up with better version. So now, before it was 2.4, now it's 2.5. So the performances, it should be okay. No Kinyarwanda available for this. I'm really unsure of the tools you can have for Kinyarwanda. Although, I mean, there are many people who speak Kinyarwanda. Could people spend resources to build something for Kinyarwanda? Maybe no. Now, if you like text mining, and if you want to contribute to this part, create a project later on, get some friends, get some colleagues, check the details, find some partners to help you to do that, and build something for Kinyarwanda. You need to do it only once. Once you have it, everybody can use it. And that's, of course, is something really nice. So people who are really interesting, like in Old French, they built a model for Old French. That's why, and that's how you have it. So it's totally possible to build it for Kinyarwanda, but you need the resources and the time to do that, and a bit of technical knowledge. So if I use UDPipe load model, now I have loaded my model in R. So it's here in my model. Now I want to process some text. So I'm going to create a variable. I'm calling it my text. And you see what I wrote? I have just bought 2 hats in Hong Kong while on vacation. Just whatever sentence you want in English. And you can have several sentences. It's okay. They're super nice. Okay, I bought 2 hats. They are super nice. So what I want now, I have my language model for English. I have the text I want to analyze. What I need to do is conduct the morphosyntactic parsing. Okay, Digital Umuganda, they are starting to do work on it. Very good. It will come, okay? With time, many more languages will be processed. So given the technological development that you can see in Rwanda, in Kigali in particular, it will be here soon enough. So then you can use it. And then you can start to analyze news articles written in Kinyarwanda. You can do a lot of things, actually. So that would be really nice. That would be very nice. So we need a third function. We downloaded our model. We loaded it into the memory. It's here. Now we use the third function. We call it UDPipe annotate. You give the model you want. So that's the language you want to play with. And then you give the text that you want. You can keep this. Don't worry too much about that. You execute that. It's done. And if you want to check it in an easy way, you just turn it into a table. So you say, take this, the result, and turn it into a data frame. It will be easier to read. Okay. We are done. Let's see the result. Okay. You see, the result is a table. It has a number of columns and it has a number of rows. Each row corresponds to one word. That's the token. And each token gets some ID. The sentence in which the token appears is repeated. So you have it each line. So you have, if you have a whole text, it will also tell you the number of the paragraph, the number of the sentence. But here we have something quite simple. Let me see. Did I do the, all right. Let me, I did something bad. I think All right. I did not enter the new phrase sentence. Okay, you can see now. First sentence, and then the second sentence. So you can see that. And then you have all the words, and each time you start a new sentence, you have the position of the words, the ID of the token in the sentence. So in the first sentence, you start 1, 2, 3 up to 13. There are 13 elements, and then you start back from 1. Here you see all the words, that's the token. And then you see the lemma. Boat, the lemma is by. Hats, the lemma is hat. What else can you, well, yeah. There, they are, the token, the lemma is the verb to be. Perfect. It works quite nice. You can also see that the dot is identified as a dot, the exclamation mark as an exclamation mark. And then you can see they call it UPOS, and then they have XPOS. They have two different systems. That's the grammatical category. That's part of speech tagging. I is a pronoun. Have is an auxiliary. Just is an adverb. To is a numeral. Hong Kong, that's a proper name, etc., etc. So it has extracted the grammatical categories automatically. And I think the XPOS, that should be the same as what we have seen here. I guess that corresponds to maybe to this. Like you see JJ, adjective, adjectives JJ. So you see, these are the 3 bank categories. Because, okay, Jessica, when you give a conjugated form of the verb, like are, is, the lemma is the infinitive form of the verb. So you get to be, yeah. But here you see that it was able to understand that it's are, right? But when you write, you can say there, and you don't say they are. It was possible to detect that. And then we have something even more. We have fits, like features. And you see that hats, for instance, it's a noun, the lemma is hat, and you can see that it's the plural. And then you can see Hong Kong is kind of singular. There, they are. You see, it tells you the mood is indicative. The tense is the present. And the verb form is, I forgot what is that, what is finite. I'm not so sure, but it gives you some information. They, it tells you, is the case is nominative, number is plural, is a third person, and it's a personal pronoun. That's really nice. It gives you all this information. And then it also helps you to relate the elements with each other, the dependencies. So you see, when you check I, the head is for, and for is both, the verb. So it relates the subject to the verb. And have and just are also related to the verb, and the verb is related to nothing because it's the head of the sentence. Two hats, you can see that two is related to the head of two is hats. Number 6. So it shows you how the words, they kind of connect to each other. And they additionally tell you the kind of relationship it is. Plus yet a little bit of other things. So it's very detailed, okay? It does not always work, okay? It's not 100% perfect, but usually it's pretty good. Is it difficult to do? No. You download your model, you load it into the memory, you download it on your computer, you load it into the memory, you have the text you want to analyze, and you use UDPipe annotate, you give the model, you give your text, and you get the answer. As simple as that. So it should work on your computer. If you create, you open RStudio, you get the code. You will just need to change the name in the code because the language model for English has changed. It's a newer one. You download it, you get the name, you copy the name here, you load it, you do the stuff, and it works. I would say it's pretty nice. And you can use it for many different things. So what you can do, you can try that. Open RStudio, download the R code, open the R code in RStudio, and let's use the code. And then you can try different English sentences, and you can check different lemmas for different words you choose. And you can check the different grammatical tags. And if you go online, you can find the meaning of all these tags. Then you can also try to trick the system. You can try, the man saw he saw the man on the hill with a telescope. What is going to happen when you enter that? Or if you use the French model, what are you going to get if you enter le boucher sale la tranche, the sentence we saw earlier on in the lecture? You can try weird semantic sentences, but grammatically correct. You can try like the stuff we played with for spell checking. If you know other languages, you may try them. And that's what you can do. Something else you can do, and I'm going to you can find this also on Google Drive. If you go to this place, you will find a tool that I have created. But if the 30 of you or the 35 of you, you all try at the same time, I don't think the server will manage. But actually what I did is I took the code I showed you and I created a small interface that you can access online. So actually you can choose French, English, or Mandarin. So let's say English. And you can type a sentence and you can process it just by clicking the button. And then what you will get is the table I've shown you. And you can also see the connections between the elements. Is an additional thing. But it does exactly the thing I've shown you. But you can use R, or if you want to play with it, you can use this simple tool I prepared for you and for other students. You can try whatever. So actually we can try French. Le boucher sale la tranche. What is the interpretation? Sale is the verb, tranche is the noun. So it shows the more likely explanation. If you remember what I've shown you in the lecture, one form is more likely than the other, I guess. And that's the form that was picked up by this UDPipe tool. Nice. Are you with me? Does that make sense? Does that sound good? I like this tool very much. I have used it a lot for some projects. I will tell you a little bit later on about them. Basically, I use this tool to analyze news articles written in French or in English, which are about the Rwandan genocide, to understand how the newspapers, they tell their readers about something like this. That's one of my research projects. And that's how I entered into contact with the center in which you are students. Okay, I like this question, of course. That's the way forward, right? What do we do when we have a table like this? What is the next stage? We are going to do that together later on. There are two directions. For instance, you can kind of analyze the style. Let's say that you have, okay, you have many, that's what I do, okay? I share with you what I exactly do. I have thousands of articles on the Rwandan genocide, thousands of them, from the 1990s to 2022 until today. What I try to do with this, once I apply the system, I can get for all the verbs in all my articles, what is the tense that is used. So I try to see, for instance, if when the journalists, they write about the genocide, whether they use more the past or the future or the present. And I can see whether this changes through time. Or with some other students, we try to use this to analyze the style of famous writers. And we use the output of this thing to create some deep neural networks. That's the input. It becomes the input for other tools. But you will see also, maybe most importantly, why lemmatization is so interesting. I will explain to you soon that when you want to build, like to extract the topics of some documents, like news articles or chapters of a novel, things like that, it's much better to work with the lemmas than to work with the inflected forms. And I will explain you in detail why. You will understand why it's the case. So playing with the lemmas is kind of better when you want to extract the meaning of large quantities of text, at least with the classical approaches. So you see, you can analyze the grammar, and then you can also analyze the meaning. And by the meaning, I mean the lemmas. So what you could do very simply, if you have a number of texts, you could compute the lemmas, and then you could compute what are the lemmas which are the most frequent. If I analyze 20,000 news articles about Rwanda today, what are the most frequent terms in these articles? Let's forget the grammatical words, okay? Let's forget they and to and the and But if I look at the proper names only, okay? I take 20,000 articles on Rwanda. I do this for all my articles. It takes a bit of time. And then I extract all the proper names and I checked which ones are the most frequent. What is the most frequent proper name for Rwanda? Is it Kigali? Is it Kagame? Are there other important persons from Rwanda that I'm going to find there? That's the beginning of text mining, right? I will get the most frequent elements. And I could see what I'm doing. I can show you later on. If I check how frequently, if I check like the frequency of a number of famous people in Rwanda, I can check through time how frequently they are mentioned in the newspapers in France or in the UK or in other countries. And if I had a morpho-syntactic parser for Kinyarwanda, I could also compare with newspapers written in Kinyarwanda in Rwanda. That would also be interesting, right? So that's one of the applications. Analyze the press. That's what I do personally. But there are other things you might imagine, of course. Does that make sense? Okay. So that's what I wanted to share with you today. And I hope that tonight, for you this afternoon, you are going to play with this, okay? Please try it at home and see, try some sentences. Try French, for those of you who speak both French and English, or maybe you speak Spanish or yet Arabic, or it depends, right? But try other languages, give it a try. And you will see whether it works well or not, and you can tell me tomorrow, okay? And then tomorrow we can do something else. But I mean, these are powerful tools to analyze documents. That's nice. That's all how also you can start to create tools. Maybe, I don't know if in Rwanda you have commercial for this tool. Have you heard of this? Grammarly. It's a tool to help you to write better. Have you heard of this? Do you have commercials for this one in Rwanda or in other countries if you are not from Rwanda? Have you heard of this tool?
Yeah, the grammar, yeah.
Yeah, I think they publicize it everywhere. So my expectations would be that you have heard of it. Yeah, you can use it, right? Behind tools like this, you have the same systems as the one I've shown you. That's also another application, right? That's another application. Grammar checker correction. Yeah. It's a little bit different as a system, but yeah. That's what you may do. So yeah, I think that's what I wanted to share with you today. So we finished the stuff we started yesterday. I told you more about syntactic processing. I showed you this, and now I hope you are going to try and play with it. So plagiarism checkers. It depends how detailed is the software. Something you can do when you do plagiarism checking is that you look for like some sentences that would reappear like nearly the same. If you want to check whether the plagiarism is a bit more subtle, yeah, maybe you would rely partly on this kind of tool or on the same kind of techniques. You could try that. Yes. Yeah, I think that could make sense. Now, I don't know exactly how it works behind. I mean, for the private software, they don't share the code or anything. But I mean, they all rely on NLP techniques and text mining. That's always the same. These are the same things under the surface, right? It's all about understanding words and how they work together in sentences, and then in different languages, of course. Any other questions before maybe we end today's session? Or are we good for today? Maybe you won't use it in the future, right? It depends. But I just want you to know that these tools are available, that you can use them in R, or you could use them in Python. They are here, they are free, good ones. And then maybe you're going to find that, oh, maybe I could use that. UPOS and XPOS, they are just two systems of grammatical categories. So the XPOS, the second one, I think is XPOS. Yeah, the XPOS is this system, is the system I showed you here. These many categories. The other one, the UPOS, is a simpler one. You have less categories. Okay, so it's just two different ways to describe the grammatical categories of the words of a given language. And these categories, they usually work across languages. So these categories, they work for French, they work for English. Maybe in some languages it's not so clear, but well, they are meant to be quite general. So it's just two ways to describe the grammatical classes. That's it. And how you get UDPipe, this system, it's a deep neural network that was trained with annotated corpora. That's how eventually it performs with any kind of sentence with a few errors. Okay. Any final thing? Okay. So I will stop the recording for today. I will.
I think I have just
sure,
a question.
Yeah.
Yeah, you say that you can analyze like the frequent words over time.
Mm-hmm.
So in that case, it means you you analyze a lemma as a variable, and then you do the normal way we do our statistical analysis, or
Sure.
there's
Yeah.
some other specific?
Yeah, exactly. Yeah. I like to use lemmas very simply. If I use the inflected forms, the token, I will have dog and dogs as different words. I think it makes more sense to say that dog and dogs, they are one form. Or if I have chanter, 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 chantat, chantation, all these things in French, I think it's better to all consider them as the verb to sing and analyze them as analyze the lemma instead. So yeah, once I have my column with all the lemma in my text, I can just use some sort of summarizing function in R, I compute the frequency, and yeah, it's data science. Data science applied to words. I can compute frequencies. It's like a categorical variable, right? Except I have many categories. And yeah, I have a range of techniques which await.
Okay. Thank you.
Yeah. Okay. All right. So I'm stopping this. I'm stopping the recordings for today.